Mana mana. Mana mana. Mana mana. Mana mana. Mana mana. Mana mana.
Let's continue using our properties of rational exponents to evaluate and simplify expressions. In our last video, we did a lot of evaluating because we actually had numbers as our bases, so we could actually come up with actual numbers for our expressions. This time, as we move forward, we'll be simplifying variable expressions. So we won't necessarily always have numbers as our bases, and we won't necessarily be able to evaluate. I can see in example B here, though, I will be able to evaluate. All right, so we're going to use all of our properties of exponents, and we're going to make sure that everything's completely simplified. Starting with A. This one is tricky. You have to be able to recognize that you have like terms here. You have two terms. Each of them have the exact same variable raised to the exact same power. And you have coefficients, 3, and in the second term, 1. So because you have like terms, all you're doing is combining those like terms. So you're adding those coefficients to get 4x to the square root of 2 power. That's all you can do. Those are tricky. But not really. You just got to recognize that you have like terms. All right, for B, there's a couple ways to approach this. Let's see. The first way I'm going to go with is trying to get like bases, because if I have like bases that are being multiplied together, then I can just add the exponents. So let's see what that looks like. So I know that 4 to the 1/4, I can also make 64 have a base of 4. And if you don't know that, use a factor tree. But 64 is 8 times 8, which is 4 times 2. I feel like we've done this before. And then, let's see, these guys will give me another 4. So really, I have a base of 4 raised to the 3rd power. So 64 is really 4 to the 3rd power, and I'll raise that to the 1/4 power. I've got 4 to the 1/4 power. I've also got 4 cubed raised to the 1/4 power, so I have a power raised to a power. I'll multiply those powers to get 4 to the 3/4 power. So now I have like bases being multiplied, which means I can add the exponents. I notice that the exponents have like denominators, so this is going to work out really easily for me. I get 4 to the 4/4, or 4. There's other ways to go about this problem. So what I notice also is that 4 and 64 are both being raised to the same power, which means I could use the power of a product property. Let's see where that is here. To go backwards. Right now I'm here, and I can go back to that. All right, so what I mean by that, if I come down here, is I could basically say, hey, this is 4 times 64, all raised to the 1/4 power. Well, 4 times 64 is 256. So now this is 256 raised to the 1/4 power, or it's the 4th root of 256, and we've done this in a previous lesson. The 4th root of 256 is in fact 4, because 4 to the 4th power is 256. Either way, you get the same answer. I prefer the first way because it's also going to be really helpful when you're dealing with variable expressions and you don't have a way to exactly evaluate this. Which brings us to C. I think the first key here is for everybody to recognize that only x is being raised to the negative 17/4. 4 is not. This can be rewritten as 4 times x to the negative 17/4. Now, if there had been parentheses around 4x, then yeah, they're both being raised to the negative 17/4. So now what I need to do is just deal with x to the negative 17/4 because you can't have a negative exponent. So I'm going to have to flip the base. All right, so 4 stays just like it was. You could write that as 4 over 1 if you want. And maybe I will. Let's see. X, however, becomes now 1 over x, and that is raised now to the positive 17/4. Now I'm going to give that positive 17/4 to both the numerator and denominator of my quotient. But 1 raised to the 17/4 is just 1. So in the denominator now I have x to the 17/4. All right, now x to the 17/4. I could get crazy right now and I could start rationalizing my denominator, but I don't think that's going to be the most helpful. I think I should try and simplify x to the 17/4 by realizing that 17/4 is an improper fraction. So let's pull out some wholes from that 17/4. And 16/4 would be a whole 4 that I could pull out, right? So I'm going to leave the 4 in the numerator. So I'll multiply straight across so that 4 times 1 is 4. And now on the bottom, I've just got x to the 17/4. I'm going to try and break that up so that I have 2 bases, one of them being raised to a power that's a whole, times another base, the same base, being raised to something that's not a whole. So I know that 17/4, I can get 4 wholes out of that because I can get 16/4. So then I need 1 more fourth in order to make 17/4. All right, so now I've got 4 over x to the 4th times x to the 1/4. Now I need to rationalize that denominator, but it's not so big anymore. I just have to multiply by x to some power that when I add it to 1/4, I get a whole, like 3/4. Do that in the numerator as well. And you now are left with 4 times x to the 3/4 over, and then you've got x to the 4th times x to the 4/4, which is really like x to the first power. All right, so now I'm left with 4 x to the 3/4 over x to the 4th times x to the 1st, which is x to the 5th. There's your final, most simplified answer. Moving over to D, I am going to use rational exponent notation on this one. I have several products here. All of these numbers all of those factors are being multiplied together. So how about I start with taking that factor of 5 times a to the 6th times b to the 4th times c to the 10th times d to the 5th and raising all of that to the 1/5 power. So now I'm going to give that 1/5 power to all the factors. So 5 gets 1/5 power. A to the 6th gets raised to the 1/5 power. B to the 4th gets raised to the 1/5 power. C to the 10th gets raised to the 1/5 power. And D to the 5th gets raised to the 1/5 power. All right, there's nothing I can do about 5 to the 1/5. That just stays. Now I've got A to the 6/5. I'll write that out for now. I've got B to the 4/5. Just using the power of a power property. I've got C to the 10/5. And I've got D to the 5/5. Okay, let's see. Try and give myself a little bit more space here. Again, 5 to the 1/5 just stays 5 to the 1/5. A to the 6/5. Well, I can get an A to the 5/5 out of that. So then I need another A to the 1/5 to make that 6/5. B to the 4/5. Well, that's not an improper fraction, and that there's no way to simplify that, so I'm just going to leave that as B to the 4/5. C to the 10/5 becomes C to the 2nd power. And d to the 5/5 just becomes d, or d to the first power. All right, so let's see here. I think I'll take everything that's to a whole and move that to the front. So what I mean by that is I have a to the first power, or a to the 5/5, which is becoming a to the first. I have c to the second power, and I have d to the first power. Everything else is either to the 5th power or to the 4/5 power. Couple ways to write this. You could leave it so that you're just like, okay, this is going to be 5 to the 1/5, a to the 1/5, b to the 4/5. I'm fine with that. You have to be able to recognize these in many different forms though. And because these last 3 factors are all the 5th root, you could also write it like this. So I could have a 5th root of 5, a, and b to the 4th. That is probably the best way to write that, but I am fine with you writing it like the above. Moving on, letter E is currently written using radical notation, and I'm going to rewrite it using rational exponent notation. So I'm going to rewrite my fraction, and now I'm going to raise it to the 1/4 power. Now I'm going to use the power of a quotient property to give that power to both numerator and denominator. So next I get the numerator raised to the 1/4 power and the denominator raised to the 1/4 power. Next, I'm going to use the power of a product to give that 1/4 to each factor in the numerator. So it's going to go to both x to the 8th and y to the 11th. X to the 8th is now raised to the 1/4 power. Y to the 11th is now raised to the 1/4 power. Z to the 6th is also going to be raised to the 1/4 power. Now from here, I'm going to take the powers and raise them to another power, which means I'm going to multiply powers. So I'll have x to the 8/4 times y to the 11/4 over z to the 6/4. So x to the 8/4 reduces to x squared. That one's nice and easy. Y to the 11/4 is not completely simplified, and it can be simplified. It's an improper fraction. Well, how many wholes can I get out of 11/4? Well, let's see. I could get 3 wholes would give me 12/4. So I think I can get 2. So I think I can go 8/4. And I'd have to have 3/4 left over. Right? 8/4 plus 3/4 gives me that 11/4. Now with z to the 6/4, I can do a couple of moves here. I think the best way to go is to reduce first, because you're going to have to reduce eventually. Otherwise, I could go ahead and figure out how many wholes I can get out of 6 using a denominator of 4, but I could also do that using a numerator of 3 and a denominator of 2. All right, I'll move up here. So now I've got x squared, y squared, and there's nothing I can do with y to the 3/4. That's completely simplified. It's no longer an improper fraction. In my denominator, however, I do have an improper fraction. How many wholes can I get with 3 halves? Well, I can get z to the 2/2 times another z to the 1/2, which gives me a total of 3 halves. So completely simplified, I'm going to end up with x squared, y to the 3/4, a z, and then a z to the 1/2. Not completely simplified though. We've got a problem here because I am not allowed to have a radical in the denominator. And really that is the square root of z, right? Z to the 1/2 is the square root of z. So I now need to multiply numerator and denominator by something that's going to make that a whole. So what I could do is multiply numerator and denominator by z to the 1/2. And the reason I can do that, let's see here. So now I got x squared, y squared, y to the 3/4, z to the 1/2, all over. And now I'll have a z to the first and another z to the first, right? Z to the 2/2, which really is like z to the first. So one last move here, x squared, y squared, y to the 3/4, z to the 1/2, and I'll have z squared in the denominator. I did a lot of moves there. You could have simplified that and made it a little bit easier on yourself, but I want to show you everything that's going on so that way eventually you can get quick at this and know all the steps and be able to do some of them in your head. All right, that was E. Let's move on to F. So hopefully you notice that you have like terms. Both of these terms have a square root of x in them. So all you're going to look at is the coefficients, 8 and -3. Well, 8 minus 3 is going to be 5, square root of x. It's that simple. G. I think I'll start this by thinking to myself, I have 2 4th roots. Are they like terms? I don't think so. Because while they both have the 4th root of 6 in them, they also both have the 4th root of x, but one of them's x to the 5th. So those are not like terms. I'm going to start off by rewriting this in rational exponent notation. So we'll have 2 times 6x to the 5th raised to the 1/4 plus, and then I've got an x times 6x raised to the 1/4. Now I'll use that power of a product property to give that power to both factors. I've got a factor of 6 and x to the 5th in the first term, and in the second term I've got a factor of 6 and x. Now 2 does not get raised to the 1/4 power. 2 is not being raised to the 1/4 power. 2 is out here by itself being multiplied to 6 to the 1/4 power. And now x to the 5th raised to the 1/4 power, hopefully you know, is x to the 5/4 power. Plus, my second term now has x, which is also not being raised to the 1/4 power, times it's got a 6 being raised to the 1/4 power, and an x being raised to the 1/4 power. Okay. From here, I think the only simplifying I can do is taking that x to the 5/4 power, because that is an improper fraction, and getting a whole out of that. So a 4/4. Which leaves me with an x to the 1/4 power. All right, plus I got an x to the 6/1/4. I don't see anything changing in the second term. Not yet anyways. All right, let me go ahead and simplify my first term. So I've got 2 times 6 to the 1/4 times x to the 1/4. My second term, I'm going to try and rewrite that in the same order. So I've also got a 6 to the 1/4. I don't have a 2, but I have a 1 coefficient there. So I could potentially say, hey, this is times 1. And then I've got an x. And then I've got an x to the 1/4 power. So do you guys notice anything now? It looks to me like I have both terms have a 6 to the 1/4. Both terms have an x to the first. And both terms have an x to the 1/4. So now they are like terms, and I'm going to combine them looking at the coefficients. I'm just going to add that 2 and that 1, and that's going to give me 3. And then you have a variety of ways that you can write this. Let me start by just keeping everything in the exact same order. However, I could take the things that are to the 1/4 power and I could put those under a 4th root radical. So let's go, I'll just go right here. So I could say, hey, this is actually 3 times x and then the 4th root of 6x. So either one of those works. They are both equivalent. This one looks a little nicer, so I think I'll leave my answer like that. Moving on to properties of rational exponents in real life, we're going to talk about the weight of whales. So the weight W in tons of a whale as a function of the length in feet can be approximated by this model. We are going to approximate the weight of a humpback whale with a length of 49.17 feet. So we know the length and we want to know the weight. And we have this beautiful formula for us. And all we're going to do is we're going to take this 49.17 and we can then plug it in right here. I don't think I would expect you to do this without a calculator. So I'm going to do this with a calculator and I'm going to use our graphing feature. Let's go to y equals and let's type in the formula for the weight of a whale. Instead of L, I'm going to use X. And I'm going to raise that to the 3/2 power. Make sure you use parentheses. Now, instead of punching in the actual weight, I can use my table of values to get any weight that I want. So I don't have to do all these separate calculations. So you can do second table set. Where do you want to start? Well, I'm going to tell it to start at 49.17. Then I can do second table. And I am getting this very long number. I just used my right arrow to get on top of it. Let's go ahead and let's round that to the nearest thousandth. So 3.173. And that was going to be in tons. And if the directions asked me how I got that or to explain how I got that, I could just write used table in graphing calc. Moving on to part B. A pilot whale is 1/5 the length of a blue whale. Is its weight also 1/5 of a blue whale? Well, we were given a formula above to find the weight of a whale. And that formula is W equals 0.1077 L raised to the 3/2 power. So if now I know that a pilot whale is 1/5 of the length, then its L is equal to 1/5 of L. All right, so I would take this 1/5 of L and substitute it in for L. Let's see what we get. Now, 1/5 times L is being raised to the 3/2 power. So now I have this extra factor in here of 1/5 to the 3/2 power, right? I have a product being raised to a power, so I'm going to give that power to each factor in the product. So I really end up with this. 1/5 to the 3/2 times L to the 3/2. So the things that have not changed from our original weight formula of a whale is the factor of 0.1077, that's exactly the same. The factor of L to the 3/2, that's exactly the same. The thing that has changed is that factor of 1/5 to the 3/2. Now, I don't think that that's the same as 1/5. Let's actually get a number for that using our calculator. So that is 0.089. Whereas 1/5, if you don't know this, is 0.2. So in fact, the weight is not going to be 1/5 just because the length is now 1/5. It's actually going to be 0.089 times. So the pilot whale's weight will be 0.089 times the blue whale's, even though it is 1/5 of the length of the blue whale.
Mana mana. Mana mana. Mana mana. Mana mana. Mana mana. Mana mana.